of the integral of B dot dA. This part is the flux, the magnetic flux, right? That's the magnetic flux. So we can write it. The flux. By the way, there is a minus sign, but I forgot. The flux dt. And this minus sign is due to Lenz. This Lenz's law. It always opposes, so there will be a minus sign. We will learn how to work with it, but for now, this is Faraday's law. And this E dot ds is the EMF, right? So this is Faraday's law. So let me write down the 4 laws that we know as we know them so far. So the 4 laws that we have learned. We had Gauss's law, E dot dA. Does anybody remember what this one is? E dot dA equals to?
Yeah, over epsilon.
Q enclosed
Over epsilon.
over epsilon naught. Yes. Now, E dot ds over a closed loop used to be 0. And it is true that it would be 0 if the flux is not changing. If there is flux, there will be an induced field. And how much is it? It's equal to minus d dt of B dot dA. That's the second. There is the third of Maxwell's equations. This one says the magnetic field integrated over area is always equal to 0. This one is also done. So we know 3 laws. Okay? Because basically this one says there are electric charges or electric monopoles that you can enclose. But for this one, the magnetic field through an area, a closed surface, is always equal to 0. Because the magnetic field lines that enter must equal to the lines that exit. You cannot just have lines exiting out of nowhere. You cannot, in other words, enclose just the North Pole by itself. You have like a North Pole that gives you magnetic field. You can't. So that's that one. Here's the third one. B dot ds is mu naught times I through. What was this one called? Due to who?
Ampere.
This is Ampere's law. This will be edited. So far it's Ampere's law, but it will be edited in a week or 2. So we have 3 complete equations, and the 4th one is still incomplete. Okay, so that's what we know so far. Our goal now is to learn how to use this one. How to use this equation. Huh?
So we still have 3 more to go.
No, we had 3.
Oh.
We still have this one to add a term to it, and then we will be done with Maxwell's equations. This is called the integral form of those equations. There is the differential form. Okay, so that's Faraday's law. Yeah, and basically says a magnetic field will induce a change in magnetic field will induce an electric field. So what we will see is, let's say you have a magnetic field coming out, right? A magnetic field coming out.
What do you call those? Integral laws?
Huh?
What were those called? Integral laws?
Oh, the 4 equations?
Yeah.
4 equations are called Maxwell's equations. So that will be, we'll discuss them in the next chapter. Okay. So here's a question. You have a magnetic field out of the board. Magnetic field is increasing. Okay. Magnetic field is increasing. Suppose I put a loop here, right? B increasing. In what direction will the induced current be? Magnetic field is out and getting larger. So I need to oppose it, so I need to produce a magnetic field in what direction? N. So how do you produce a magnetic field? N? Clockwise current. So the current must be clockwise. Now, what pushes charges to make them go clockwise in this direction? Who's pushing them? Yes, it's not the magnetic force, it's the electric field. So in fact, the electric field will be going in circles. Electric field will be in circles. We'll see how to calculate it. I'll stop here.
Just the positive discharges.
Huh? No charges. Yeah, there are no charges here that produce this electric field.
So it's like a magnetic force separates the positive and negative charges inside the wire that's producing an electric field, which
No, even without a current field at all, there would be a electric field circulating around this magnetic.
Wait, what?
Yeah. No, I need to stop this thing.
Yeah.